Okay, uh, today we will start this topic called SHM. Basically, it's a very important topic from IIT JEE point of view called simple harmonic motion. Now, there are different types of motion actually. For example, we have rectilinear motion, which is motion in a straight line, curvilinear motion. We have already seen in rotation uh, things like translation, fixed axis rotation, plane motion, and so on. So simple harmonic motion falls under the category of an oscillation. So for example, you have two types of motion. One is what is called periodic. Periodic motion means this motion keeps repeating itself after certain regular intervals of time. So I can say this repeats itself at regular time intervals. That is periodic motion. Then you have oscillatory motion. I can say this motion is to and fro motion. Something moves forward and backward like a pendulum or a swing. Now, simple harmonic motion is also periodic, is also oscillatory, plus something more. It's something more. In fact, the motion of Earth around Sun is periodic. It completes one revolution around Sun in 365 1 by 4 days. So that is a periodic motion. The motion of Earth is repeating every year. If it doesn't repeat, we are doomed. There are no seasons and nothing. Even the motion of Earth about its axis is periodic. It takes 24 hours to complete one rotation. Then you can have oscillatory motions, which is to and fro. This to and fro motion need not be periodic. Need not be periodic. Okay, you can move something to and fro in a non-periodic way. So that is oscillatory. So periodic motion is something which repeats at regular intervals of time. Periodic motion need not be oscillatory. For example, motion of Earth around Sun is not oscillatory, it's only periodic. So both these are unrelated, they are independent. But SHM is also periodic, is also oscillatory, plus something more. We will see what is this something more later. So simple harmonic motion is a motion which is periodic. It has a regular period. The motion repeats at regular intervals of time. It is also oscillatory, that means there is to and fro motion and something more. In fact, if you want me to exactly categorize what is SHM, it is a motion where the force acting on a particle is proportional to the displacement of the particle and directed opposite to it. Okay, this is the simple harmonic motion. Here I am representing displacement with an x coordinate, but you could also represent it with r. Whatever it is, force is proportional to displacement and directed opposite to it. So if force is proportional to displacement and directed opposite to it, I can say acceleration, I'll take one dimensional motion, that will be easier, is proportional to displacement and directed opposite to it. So this is the criteria for simple harmonic motion. So if you want to prove that some motion is simple harmonic, apply Newton's second law, calculate the acceleration. If you find it is proportional to the displacement and directed opposite to it, that is simple harmonic. For example, the best example for simple harmonic motion is a spring block system like this, with this block on a smooth surface. This block has mass m and there is a spring of spring constant k. It's an ideal spring. Ideal spring means the spring is massless and Hooke's law is valid for this spring. So if you have such a system, suppose I pull this block by a distance x. So originally the spring was in its natural length and I am pulling this block by a distance x here. So the spring got expanded. Now spring starts applying a force like this, kx. So you see the displacement given to the block was to the right, but the force acting on the block is to the left, and it is also proportional to x. The spring force depends on x. More is x, more is the spring force. So force is proportional to displacement, directed opposite to it. Okay, directed opposite to it. So this is the criteria for a simple harmonic motion. I'll put an arrow on this to show that force is opposite to displacement. So in simple harmonic motion, force is dependent on displacement. More the displacement, more the force. Also, if displacement is to the right, force is to the left, and if displacement is to the left, force on the body is to the right. So if force is proportional to displacement, I can say acceleration is also proportional to displacement and directed opposite to it. Now I can introduce a constant. Acceleration is minus some constant into x. Whenever there is a proportionality, I can convert it into equality by introducing a constant. The constant here should be positive, because if the constant is negative, then the minus sign becomes plus. Then acceleration is not opposite to displacement. So the constant, I am going to write it as omega square, because square is always positive. I want a positive constant, so there is nothing better than representing it by square of some number, because square of a real number is always positive. It may be 0 if the real number is 0, but so at least it is not negative. So this is the starting point for our discussion on SHM. So in SHM, acceleration and displacement are directly proportional to each other, and acceleration is opposite to displacement. The minus sign shows that. So A is minus omega square x, where omega square is the proportionality constant between acceleration and that displacement. Okay, this is our starting point. Now in every topic in mechanics, our aim is to get a position time relation. This is our aim in the whole of mechanics. For example, even in kinematics, our aim was to get the position time relation for a particle. So we want to know how the position of particle changes with time. Once you know this, you can get velocity time relation by differentiating this, and you can also get acceleration time relation. So once we get position time relation, our problem of mechanics is solved. So our whole aim is to get this position time relation. Of course, here I have acceleration position relation. So somehow from here I must get position time relation. Let's go further into this. A is minus omega square x. Let's take this equation and go a bit more into it. So we have A is minus omega square x. Okay, I am considering a case where a particle is moving along x-axis. It's a one-dimensional motion, and A is nothing but rate of change of velocity. dv by dt is minus omega square x, and v is nothing but rate of change of position. So v is again dx by dt. I am replacing v with dx by dt. This is minus omega square x. So this is a second derivative of x with respect to time. So d2x by dt square is minus omega square x. It's a second derivative of position with respect to time. Let us see what this equation tells us. If you differentiate position 2 times with respect to time, you are getting back again position. Okay, this is the idea. So there is some position time relation. I don't know what it is, but if you differentiate this position twice with respect to time, you will again get back position. For example, let us say x is t square. When you differentiate it first once, you get 2t. When you differentiate it once again, you get 2, but you don't get back again x, because x is t square. If you had t square here, you would have got x. So by differentiating 2 times, I am not getting what I originally started with. Okay, normally this is the case, but in SHM, if you differentiate position twice, you get back the position. Of course, it is multiplied by some constant, some number like omega square. So we have to find an xt relation such that if you differentiate it two times, you will get back x. Let's take a guesswork. X equal to t square doesn't work. Okay, you don't get back x after differentiating two times. That doesn't work. What is the function which when you differentiate gives back the same function? Let's try to see that. For example, if I say x equal to e power t, suppose you have this, differentiate it once, dx by dt gives back e power t again. Even d2x by dt square, differentiate once again, gives back e power t. But it doesn't give a minus sign. We want a minus sign also. d2x by dt square must be omega square x. You also want omega. Let us see another example. Suppose if I take x, e power minus omega t, if you differentiate it once, you get minus omega e power minus omega t. If you differentiate it once again, you get it as omega square e power minus omega t, but e power minus omega t is x, so omega square x, but minus sign is missing again. So even this solution doesn't work. In fact, there is a relation between this equation, this is the SHM equation, second derivative of position gives back position with a minus sign. So there is a relation between this equation and complex numbers. In fact, if you take x as e power I omega t, where I is square root of minus 1, it's a complex number, then if you differentiate this once, you get I omega e power I omega t. If you differentiate it once again, you get I omega whole square e power I omega t, and e power I omega t is nothing but x, so I square omega square x, but I square is minus 1, I is root minus 1, so I square, this complex number gives you minus 1, so minus omega square x. So I get it. So d2x by dt square, I get it as minus omega square x when x is I omega t. So there is a complex solution to this differential equation. So this equation, what we have seen here, this is called a differential equation. Differential equation. You will learn it in mathematics, differential equations, but this is even more strange. It is a second order differential equation because there is a second derivative of x with respect to time. So it's a second order differential equation, and normally you don't learn about second order differential equations in your math course. They are not to be learnt at this level actually, but we cannot avoid them in physics. You will be learning about these equations in your engineering, maybe your second year of IIT and so on. Sometimes you do a whole course on differential equations. You even do nth order differential equations and so on. So the solution for that equation is complex. But later when you learn complex numbers, you will know that e power I omega t can also be written as cos omega t plus I sin omega t. There is something called De Moivre's theorem and etc. etc. This you will learn a proof for this actually even in your math course. So I can say even cos omega t, the real part of this complex number, satisfies this differential equation. This, which one? d2x by dt square is minus omega square x. This equation. Even the imaginary part sin omega t satisfies this differential equation. Let's check that. So let's see whether cos omega t satisfies this equation. X equal to cos omega t. Differentiate it once. So dx by dt gives you minus omega sin omega t. Differentiate it once again with respect to time. So d2x by dt square gives you minus omega square cos omega t. So cos omega t is again x. So it gave back you x, but with a minus sign. So second derivative of x with respect to time gives you back x. This is possible when x changes with time as a cosine function. When the xt relation is cosine wave, then this is possible. Similarly, when xt is a sine wave also, doesn't matter. Even then it satisfies this equation. So if you differentiate it first time, you get omega cos omega t. You differentiate it once again, so you get minus omega square sine omega t, but sine omega t is x, so minus omega square x. So ultimately, when you end up with this differential equation d2x by dt square equal to minus omega square x, the xt relation, the solution to this equation is a cosine or a sine, x equal to cos omega t or x equal to sine omega t. These cos and sine are given a special name. They are called harmonic functions. Okay, sine and cos, these are called harmonic functions, and that is the reason why this motion is called simple harmonic motion, because the solution to the differential equation that you get here is a harmonic function, and it is a simple harmonic function. Obviously, when I am saying it's a simple harmonic motion, there is also a complicated harmonic motion. It is called damped simple harmonic motion, and even there are other complicated motions also, which we won't take up here. So ultimately, to summarize it to you, simple harmonic motion is a motion where acceleration is given by minus omega square into x, some constant, some positive constant, minus of some positive constant into x. You can write it as d2x by dt square equal to minus omega square x, or d2x by dt square plus omega square x equal to 0. So by applying Newton's laws, if you get acceleration to be proportional to displacement, or if you get this equation, then that is SHM. So in many cases, when somebody asks you, prove the motion is SHM, apply Newton's laws and prove that acceleration is proportional to displacement. Over. That is our whole idea. Now the solution to this equation, when I say solution, it is a relation between x and t, we saw will be cos omega t or sin omega t. But more general solution is a cos omega t plus phi, where a and phi could be anything. Still it satisfies this equation. So x equal to a cos omega t plus phi, or you can say even x equal to a sin omega t plus phi. Any one of them, it's up to you. Both satisfy this equation. So that is the solution. Now you might ask, what is the value of this a and phi? You can have n number of values for them. Okay, any value of a and phi will satisfy this equation. Now these are what are called unknown constants. Why are there two constants? Because it is a second order differential equation. When you start integrating and doing things, you get two constants, two unknown constants. If it is a first order differential equation, for example like dx by dt equal to t, then you can say x equal to t square by 2 plus some unknown constant c. There is one unknown constant. Okay, so if it is a first order differential equation, there will be one unknown constant, but this is a second order differential equation, so there are two constants, which is a and phi. So this is the whole idea, but let's try to do it in a more rigorous way. Right now what we have done is, we got this equation d2x by dt square plus omega square x equal to 0. Okay, what is d2x by dt square? It is acceleration. Second derivative of position is nothing but acceleration. First derivative of position gives you velocity. Once again, if you differentiate, you get acceleration. So this equation, this is the equation, and we saw the solution is x equal to a cos or a sin omega t plus phi. We did a guesswork and got to this solution, but I want to derive this in a more rigorous way. Okay, that's what I am planning to do now. So what we will do is, we can write it as d by dt of dx by dt, that is the meaning of second order derivative, plus omega square x equal to 0. So d by dt of dx by dt is v. Now we can write this as dv by dt plus omega square x equal to 0, acceleration plus omega square x. I can write this as dv by dx into dx by dt plus omega square x equal to 0. Why am I writing it like that? You see, I cannot solve this equation that easily because x is a variable, V is a variable, t is also a variable. So there are three variables here. I want to somehow make it into two variables. If you have two variables, you can take one variable on one side of equation, other variable on other side. For example, dx by dt equal to 4. X is a variable, t is a variable. So keep dx this side, take dt that side. Then when you integrate, it's easy. There are only two variables. Here there are three variables. So I'm trying to convert it into two variables by using this technique. So I'm writing dv by dt as dv by dx into dx by dt, but dx by dt is again v. So v dv by dx plus omega square x equal to 0. V dv by dx plus omega square x equal to 0. So now if you see this equation, I have only two variables. One is v, one is x. So it should be easy to integrate this. So let's see how to integrate that. V dv by dx plus omega square x equal to 0. So we have v dv equal to minus omega square x dx. Let's try to integrate this, and I want to use definite integral here. When x is a, let us say velocity is 0, and when x is x, velocity is v. Let's try to understand these lower limits. When x is a, velocity is 0. Why is that? Suppose if you take a spring block system, which is the best example for SHM, I have pulled this by a, let us say, and I have released here. So after pulling, when you release it, speed is 0, and a is the maximum displacement from this position where spring has natural length. We call this amplitude of SHM. We'll see this in greater detail later. But when x is a, I have released the block, so speed is 0. And when x is some x at some intermediate position, I want to find the speed. So from acceleration position relation, if you see here, this equation is acceleration position relation. From that, I am trying to get a velocity position relation. Okay, so I am going closer to my aim of getting xt relation. So I have ax relation. From this I get to vx relation. From that I get to xt relation. This is my scheme that I am following. So from acceleration position relation, I am getting one step closer to solution. I am getting velocity position relation. Then from velocity position I will try to get xt relation. We will see how. So already from acceleration position relation I am getting velocity position relation. So you get v square by 2 on integration. This is minus omega square by 2 x square minus a square. This is what you get. Or you get v is omega root, I'm sorry, this is v. V is omega root a square minus x square. There could be a plus or minus here, but I don't want to take the minus sign right now. You can take it, there is no harm. I want to take the plus sign. V equal to omega root a square minus x square. So from an acceleration, this is an acceleration. We have written it as v dv by dx. From acceleration position relation, I got velocity position relation. This is the first step. I got velocity position relation. Now we can write v as dx by dt equal to omega root a square minus x square. Now I am going a step further and trying to get xt relation. Again I have two variables. X is one variable, t is another variable. So let's try to do that. So dx by dt is omega root a square minus x square, which implies dx by root a square minus x square is omega dt. Let's integrate. I will do an indefinite integral now. You can even do definite integral, doesn't matter, but this integration you will learn later. It is sine inverse x by a. You will learn it later. This gives you omega is a constant. Why omega is a constant? Because it is proportionality between acceleration and displacement. Remember, we wrote it as omega square. Proportionality between acceleration and displacement, we took it as omega square. It's a constant. So it is omega t plus some other constant phi. When you do an indefinite integral, you will get a constant. So x by a will be sine omega t plus phi. So you can see x equal to a sine omega t plus phi. So I got my solution to the differential equation, which is I got an xt relation. So from ax relation, from acceleration position relation, I first got velocity position. Further integration gave me position time relation, and my problem of kinematics is solved. So ultimately in kinematics we want to get position time relation. We want to find where is the object at a given time. You can find that if you get this relation. So we are done with that. So ultimately in SHM, position changes with time as a sine function or even a cosine function. It doesn't matter. For example, if phi is pi by 2, this becomes cos. Sine pi by 2 plus omega t becomes cos omega t. So it doesn't matter. Phi determines whether it is sine or cosine. Both are called harmonic functions. So in simple harmonic motion, the position time relation is a harmonic relation. It's a cosinusoidal or a sinusoidal relation. That is the idea of this simple harmonic motion. So again, to concisely summarize you the things, a motion is simple harmonic if acceleration is proportional to displacement and also acceleration is oppositely directed to displacement. The more the displacement, more the acceleration, and it is oppositely directed. So we wrote acceleration as d2x by dt square. Okay, so d2x by dt square should be minus omega square x. So second derivative of position gives back the position again. That is SHM. That is the idea of SHM. Second derivative of position with respect to time gives back again position. Then our next aim was to find the solution to this SHM. When I say solution, I want an xt relation, and on guessing or by doing this integration 2 times, we got this as the solution. Okay, so this is the idea. Now let's see some interesting things about this solution. So we had landed up with x equal to a sine omega t plus phi. Let's see what are all the terms involved here. X is the displacement or position, whatever it is. There is a fine difference between both displacement and position. But if I take the initial position as origin, then final position and displacement both are same. So x is displacement. A is called amplitude. You can also say it is maximum displacement from mean position. Now this brings up a question, mean position. What is mean position? Mean position, or sometimes it is called equilibrium position. Equilibrium position is that position where net force is 0 for a system. So the position where net force is 0, that position is called mean position or equilibrium position. So from equilibrium position, if you pull a block, then the maximum distance to which you pull it, the maximum displacement to which you pull it is called amplitude. This phi is called phase constant. We will see the implication of this soon, but it tells you from when you started observing the motion. Phi tells you from when you started observing the motion. T is of course time. Omega is what is called angular frequency of SHM. It's a very important quantity. Somehow this tells you also something about the time period of SHM. We are going to see that later, but this omega is going to tell you time period of SHM. So simple harmonic motion. So whenever a motion is SHM, you must assume this xt relation and then proceed with the problem. That is the idea. So you must assume this position time relation and then go with the required solution. So position time relation in SHM is sinusoidal function. That is a very important point. Now let's go further. We have this x equal to a sine omega t plus phi. Let us see this equation in the context of a spring block system like this. So I have a spring connected to a block placed on a smooth surface. There is no friction right now. Smooth surface. Spring constant is k. Block has mass m. This is an ideal spring. So this is the best example for an SHM. This is spring block system with spring and block horizontal. This is the best example for SHM. Now when the spring is relaxed, this position of the block when the spring is relaxed is called mean position. Why it is called mean position? Because at this moment, if you draw the free body diagram, there is mg, there is n, and anyway both add up to 0. So net force is 0 here. Spring is not expanded, it is in natural length. So the position where net force is 0 is called mean or equilibrium position. Now from equilibrium position, I have pulled this block to a distance a and released. So what will happen? This block starts coming down. So if you take this as x equal to 0 origin, this is x equal to a. So maximum value of x is a. In fact, maximum value of x is a. That happens when sine omega t plus phi is 1. Remember, maximum value of sine is 1. So I have pulled this block by a and released. So a is the maximum displacement from mean position called amplitude. So if I release block here, it starts moving. Okay, and by the time it comes to mean position, it gains kinetic energy. Why it gains kinetic energy? Because spring potential energy has decreased, so it gains kinetic energy. So at mean position, even though force is 0, it has kinetic energy, speed. So it continues to go to the left, and as it continues to go to the left, it pushes the spring. So spring starts applying a force to the right, and eventually it stops on this side exactly at a distance x equal to minus a. So you see, when sine omega t plus phi is 1, x equal to plus a, and sine omega t plus phi is minus 1, x equal to minus a. So the motion happens between x equal to plus a and x equal to minus a. So this block keeps oscillating like this. Okay. So if you write the force equation at any moment, suppose when the block was here at a distance of x, that means the spring is expanded by x. Okay, the block went from x equal to 0 to x equal to x. That means the spring got expanded by x. So if you draw free body diagram, there is a force kx by the spring. So this force is mass into acceleration, but with a minus sign, because displacement x is to the right, whereas acceleration is to the left. So displacement and acceleration are oppositely directed. So a is minus k by m into x, and we saw at the beginning of the lecture that a proportional to x, and the proportionality constant is what we call as omega square. So in this case, omega square is k by m for a spring block system. So you can see acceleration proportional to displacement, directly opposite to it. So the spring block system is a very good example for simple harmonic motion, with omega square is k by m, or omega equal to root k by m. So the value of omega for a spring block system is root k by m. So if you want to write the equation for spring block system, position time relation can be written as a sine omega is root k by m t plus phi. Now a is of course the maximum distance to which you pulled the block and released. So that is in your hands. If you pull it by 10 centimeters, a is 10. If you pull by 5 centimeters, a is 5. What about phi? Suppose you released and then on your stopwatch. So your stopwatch shows 0 seconds when the block was here at x equal to a. So at t equal to 0, if x is a, phi should be pi by 2. So phi depends on when you are owning your stopwatch. For example, after the block comes here, if you on your stopwatch here, then at t equal to 0, x is 0. So if you put t equal to 0, x is 0, then you can get phi. X is 0, t is also 0. So sine phi must be 0, or phi is 0. So if you on your stopwatch when the block is at equilibrium position, phi is 0. But if you on your stopwatch when the block is at extreme position, that means at t equal to 0, when you on your stopwatch, block is at x equal to a. So put t equal to 0, x equal to a here. A equal to a sine phi, or sine phi equal to 1, or phi equal to pi by 2. If you put phi pi by 2 here, a sine pi by 2 plus theta will be cos root kt by m. So it can be either sine or cos. The value of phi is determined by when you started observing the motion, when you switched on the stop clock. When the block was at mean position, if you switch on the stop clock, your phi is 0. So phi is telling you from when you started observing the motion. So it is called phase constant, and it depends on from when you started observing the motion, which is the initial condition. Okay, so we have seen all the terms in this SHM. Now let us see something about this omega. It's a very important quantity. So let us see something about this omega before we go into more advanced simple harmonic motion. So we started with acceleration proportional to displacement and directly opposite to it. So acceleration is minus some positive constant, which I write as omega square into x. So you have an acceleration position relation. After you solved the equation, you got position time relation like this, a sine omega t plus phi. Okay, we did integration twice, or you can also say we got it by guesswork. Anything is fine. Now let us see what happens if I replace t with t plus 2 pi by omega. Let us see what happens. So this equation is giving you the position or x at certain time t. Okay, now I want to find what is the position at a time t plus 2 pi by omega seconds. So at t seconds, position is a sine omega t plus phi. At t plus 2 pi by omega seconds, after a 2 pi by omega seconds have gone by, what is the position? Let's try to see that. So x will be a sine omega into, so instead of t we now have t plus 2 pi by omega plus phi, which is a sine omega t plus 2 pi. I am multiplying each term with omega plus phi, and adding 2 pi to sine doesn't make any change. Okay, for example, sine theta is same as sine theta plus 2 pi or sine theta plus 4 pi and so on. Even multiples of pi will not make any difference to sine. So I can write it as a sine omega t plus phi only. That means whatever is the position at t seconds, same is the position at t plus 2 pi by omega seconds also. That means after every 2 pi by omega seconds, body comes back to same position. It is coming back to same position. So I can say 2 pi by omega is the time period of the SHM, or t equal to 2 pi by omega. I use capital T for time period. So this omega is very crucial because it is telling you the time period of SHM. What is omega? This proportionality constant between acceleration and position. For example, if you go back to our spring block system, we got omega as root k by m. So for a spring block system, the time period will be 2 pi by omega 2 pi root m by k. This is the time period of a spring block system that we have seen previously. So the time period of a spring block system depends on the mass of the block and the spring constant of the spring. Only these two factors tell you the time period. Please note, time period is independent of amplitude. That's the strange thing about SHM. Okay, for example, I have a spring block system like this. I pull it by 1 centimeter and release it. Suppose it takes 2 seconds to oscillate. 2 seconds, 2 seconds. If you pull it by tomorrow 10 centimeters, still it takes 2 seconds to oscillate. That's the beauty of SHM. You may pull it by 1 centimeter, it takes 2 seconds. You may pull it by 10 centimeters, it still takes 2 seconds. The point is, when you pull it by 1 centimeter, the spring force is less because you have pulled it only by lesser distance. The acceleration is less. The speed the block gains is less. So the block is moving with lesser speeds. Like this. See my hand? It's moving slowly. But if you pull it by 10 centimeters, spring expands by huge amount. Force is more. So it moves faster now. See my hand now. It has to cover more distance, but it is moving faster. So it still takes 2 seconds. This also takes 2 seconds. This also takes 2 seconds. So time period is given by 2 pi root m by k. It doesn't depend on, t doesn't depend on amplitude a. So that's the spectacular thing about SHM. So in SHM, time period is independent of amplitude. independent of amplitude. This is a very important result. In fact, at the beginning of the lecture I told you that the criteria for an SHM is it is periodic plus oscillatory. Then if you remember, I wrote plus something more, periodic plus oscillatory plus something more. This something more is this fact the time period is independent of amplitude. That is what I wanted to tell you at that time. That is what I meant by more in that situation. So time period is independent of amplitude. This is the idea of SHM. So we have introduced SHM to you. So you go through this lecture once again, and my idea is I will continue this with more concrete theory and some more examples, and we'll wrap up this topic.